Okay, I'm going to do a video about determining concavity in functions. So if you remember from, I guess, geometry or early arithmetic, I guess, you probably learned about like convex, concave shapes. And if you remember, concave is like a cave, I guess. It goes inward, dips in, and then convex goes out. Another shape that's used for this a lot is a chevron because you have concavity right here where it comes in, and then it's convex out here, it comes out, or it has a protruding end. So in a way, thinking of this when you start thinking of functions is helpful because what you have is concave. So both of these in calculus are considered concave, even though you might see this being convex and this being concave, but you have to remember that in math you can kind of move your coordinate plane around a little bit, and that's going to change the perception of how you're looking at the function and what you perceive to be concave or what you perceive to be convex. So because of that, what you typically think of concave going inwards is concave up, actually, because these two ends are facing up. That's concave up. When it's something that you would kind of, I guess, consider convex, where you have something protruding out, that's going to be concave down. And then if it's just flat, there's no concavity is equal to 0, that's concave flat or concave 0. That's all there is to this. So I'm going to, like what I've been doing, and give you an example problem, walk you through how to determine concavity, and then I'm going to go back through and explain this in more detail. Okay, so if you've seen some of my other videos with the first derivative test determining increasing and decreasing functions, this is a lot of the same idea right here. So what you're going to do first is you are going to take the derivative of first and second derivative of this equation right here. So we have f prime of x is going to be equal to, let's see, 6x minus 3x squared. And then we're going to solve for 0. 6x minus 3x squared, set it equal to 0. We are going to get, let's take out 3x. So now we have 2 minus x equal to 0. And then this x is going to be equal to 0. And this x right here, x minus 2 equals 0. Let's move this to the other side, so then we have x equal to negative x equals negative 2. Divide out our negatives, we get x equals 2. So again, these right here are our critical values. And our critical values are going to tell us the interval that we're looking in. Okay? So our interval from here is going to be negative infinity to x to 0. Then we have 0 x to 2. And then finally we have 2 to x to infinity. And again, if you watch any of the earlier videos or you understand finding the decreasing and increasing functions, this will make more sense to you on why I have this placed like this. Okay, test values. I'm going to use x equal to -1, x equal to 1, and x equal to 3. And then now this is where it changes from our determining increasing, decreasing functions. We're going to use the second derivative equation, sine of the second derivative x. So the derivative of second derivative of this equation is going to be 6 minus 6x, right? So f double prime of -1, this is going to be 6 minus 6 times -1, which is going to be 6 plus 6, which is 12. Here we're going to do 6 minus 6 times 1. We're inputting our test value. This is giving us 6 minus 6, which is 0. And then here we are getting 6 minus 6 times 3, which is going to be equal to 6 minus 18, which should give us -12. Yes, -12. So here what we have is, now we know this is concave up. This one doesn't work, so we can either say test does not work or concave flat. It depends on what your teacher wants you to do here. That's really just goes by teacher. And then this is down. Okay. So now I'm going to explain this to you in a little bit more detail. What we have here is, when you're determining concavity, when we determined our increase up and down, oops, that's a little bit of a messy graph. What we did was we took the derivative of an equation, and then we found out where it intersected. Or sorry, the slope. We found the slope and where it intersected to see our points, to see like sorry, I can't think of the word right now, but we determined if it had a positive slope, we knew it would have a increasing, it was an increasing function. If it went down, we knew it had a decrease, it was a decreasing function. So sorry, these were the minimum and maximum points, and we knew that by where they intersected on our graph. Okay. So same thing's kind of true with our concavity. Now I'm going to explain this a little bit better using a x cubed graph, and you'll see that shortly. So if I take an x cubed graph, let's see if I can draw this right, and then we take the derivative of that, we are going to get a parabola. Now where our parabola intersects, that's going to tell us our points on our first derivative. This is f prime of x. That's going to tell us our minimum, our relative minimum point right here. And it is going to tell us where this is increasing and decreasing. So like here we can see it's decreasing, there we see it's increasing. So you know that now. And then when you take the second derivative of this, what you get is a straight line. This straight line is going to tell us two things. It's going to tell us our point of inflection, where it changes at. And then it's also going to tell us by having either a positive or a negative slope, our tangent line, that's going to tell us where it's going concave in, or concave up, or concave down. Because you can see our function looks a lot like half of a parabola, just one half got stuck below. Right here, if you flipped it up, it would look a lot like a parabola, right? So that's our point of inflection, where that changes over. And that'll get explained a little bit more in one of the next videos about second derivative test. But this is just determining concavity. And this line right here, its slope either being m being plus or m being negative will tell us if it's up or down. If m equals 0, it's either going to be flat or doesn't work, like test doesn't work on there. So that's what we know from here. Okay, so flipping back to our problem. What we are doing here is we are simply just finding our intervals that we're looking specifically at. So we know now that we're looking at the interval here from the critical value x point on, critical x point value over here to find to determine where we want to look at this tangent line from to see an x points beyond there. Because if we take an x point from that interval, we will know it's true for all points within that interval if it's going to be concave up or down. Okay, so then I'm just taking my critical values and putting them into my intervals. We start with our smallest critical value, which is going to be our negative infinity, because remember, most of these graphs go on to negative infinity and to positive infinity. They don't have endpoints. So we're considering that kind of our smallest critical value. And then we go to our next smallest critical value, and then that smallest critical value kind of just gets shifted over to the end of it. So we're looking from, I guess you could be like, okay, so we're going on to negative infinity, and we stop at 0. And we have to pick up right where we left off. So now we're looking at 2, so from 0 to 2. And now we have to pick up where we left off next over here. So we're going from 2 to infinity. Some teachers do like a number line, if you write it out as a number line. Personally, I don't like doing that, but I know a lot of teachers do prefer it. I'm unsure of how to properly explain that because I find it to be messier looking for myself. But if that's the way you prefer to do it, go ahead. But I'm just going to be showing you with this. It's the same general basic idea. Okay, so then I'm finding a test value within this interval to just test out in my function. So x of negative 1, it's less than 0 and it's greater than negative infinity. 1 is greater than 0 and less than 2, and 3 is greater than 2 and less than infinity. And then I plug it into f double prime. So I found f double prime, our second derivative, and I just plugged it in. And I'm just plugging in x points into this graph right here. I'm seeing where it's negative. If it's negative down here and here, we know it's going to be, that's where it's going to end up being a concave down, concave up. Just to let you know, I'm sorry, these graphs don't necessarily match up. This should actually be facing the other way. I drew this incorrectly. But ideas there, if it makes sense. Basic ideas still. And then I plug in my next test value right here, and I just plugged it in to x. And then same thing here, plugged it in, test it. And then our conclusion, like I said, you figured it out, it was up because this is positive. This one is 0, so we don't know what it is. It's probably just that flat little portion right here, right? And then here, plugged it in, and we saw that it's negative, so we know it's down. So this is this area right in here. This is probably this area right here. That's all there is to determining your concavity. I'll post another example video about this in a little bit, and this is kind of your precursor to your full second derivative test, and I'll post a video of that later on as well. I hope this was helpful.